Alright, next we're going to find the volume bounded by the plane c equals x, y equals x, and x plus y equals 2. Alright, again, what I can do is solve one of these equations for, so I'll solve this equation for, either x or y. So let's just go ahead and say y equals 2 minus x. Now I want to set these two equations equal to each other, so 2 minus x, to see if where they could intersect, and it looks like they're going to intersect at, I'm going to add that x. 2x equals 2, so x equals 1. So they will intersect at x equals 1, and when I plug that in for both, I'm going to get, 1. When I plug x in, I'm going to get 1. So therefore, when I draw my graph, alright, looks like I'm going to have intersections at 0 and positive 1 on the x. But it looks like, from this equation that I have right here, I'm going to have a y-intercept of 2. So I'm just going to go up to 2 and 1. And I'm going to go ahead and draw that line. And so I know that there's an intersection here. So y equals x is going to give me that line. And I know that y equals 2 minus x is going to give me, that line. Say 2 is where it crosses on the x-axis. And so I'm trying to find where it's bounded by z equals x, y equals x, and x plus y equals 2, and z equals 0. So just that region right there. Alright, now let's go ahead and find the volume. So the volume is going to be given by, again, I can choose, and since I have both my equation in terms of y, I want to make my x go from 0 to 1, and that means, again, this is y equals 2 minus x, and this is just y equals x, so top bottom, so 2 minus x, and y, so y equals 2 minus x, y equals x. I'm going to go ahead and put in my function, which you're going to have is just x dy dx. And now what we're going to go ahead and do is we're going to go ahead and integrate. So we're going from 0 to 1, and we have integrate that with respect to y, just xy, x, 2 minus x, dx. Clean that up, 0 to 1. We're going to have 2x minus x squared minus, plug in x squared dx. So we're going to have the interval of 0 to 1, 2x minus 2x squared dx. Integrate that, we get x squared minus 2/3 x cubed, 0 to 1. Looks like we're going to get 1 minus 2/3. It's just going to give us 1/3. Alright, next, let's get to the region of integration and change the order of integration. So, example 6, we have from 0 to 1, and then pi over 4 and arctangent of x. So what I'm going to do is, again, that first is x equals 0, x equals 1, based off of, what's inside, what's outside. So that means that y is equal to pi over 4, and y is equal to arctangent of x. Again, if you're having trouble figuring out what these graphs look like, you can always use a graphing calculator to tell what it should look like. So I'm going to go ahead and make an xy plane, and I'm going to go ahead and go from 0 to 1 on x, And then I'm going to go from y equals pi over 4. And I'm going to do my arctangent function. So I'm just going to go up to pi over 4. Make that pi over 2. Alright, the reason that is just so I can graph it, because I know that it's not going to touch there. It's going to have a horizontal asymptote there. Alright. I know it's going to intersect there. So I'm going to go ahead and draw that. So, draw it in orange. Try to draw that as best as I could. This is not the greatest picture of it. And that equals pi over 4. So what we have here is this region right there. Alright, so once again, I'm going to do x on the outside, because x is already defined by 0, 1. 0, 1. And my y is already defined as y equals arctangent of x. It's on bottom. And pi over 4 on top of our function. And in this case, our function is just f of... Oh, I'm sorry. It just wants us to change the order. So that's just giving the picture. I'm just actually going to do it. And then I just realized, okay, all I got to do is change the picture. All right, well, if I'm going to change this, I had to realize what it looked like first. And so now what I can say is, well, the lowest value that it goes for y is going to be 0. Highest value for y is going to be pi over 4. And then I can solve this function right here. Y equals arctan x. I can solve that for x. I'm just going to do tangent both sides. So x equals tangent y. So this is what we're given. So the way I can rewrite this is going to be the integral. I can do my y's first, which are going to be 0 to pi over 4. And then again, when I do my x's, all right, I'm going to go from furthest left, all right, for my x. Furthest left for my x is going to be 0. Furthest right for my x is going to be tangent y. F of x, y, and then now I'll say dx, dy. And so that's the solution. Whoa, I want to make that a little bit bigger. All right, I'm going to go ahead and do the last example. Next, and all we have to do is reverse the integration. All right, we're going to change it up, and then after that, we're going to do it. So just adding another step to this. So let's go ahead and write what we have. We have y is equal to 0, and y is equal to the square root of pi, I believe. And then the next one we have, or because that's the outside, and then the inside is going to be x equals y, and x equals square root of pi. So this gives me an idea of what it looks like. And so I'm going to go ahead and sketch this region. And it looks like we're going from 0 to the square root of pi over 4. I'm sorry, it's the square root of pi. And then we have our function x equals y, and it's also going to go from the square root of pi. So we have y equals x. This function right there, let me change up the colors. I want to make it straight. There we go. whatever. I don't have much time till class starts. Y equals x, and this is x equals square root of pi. And so then this is my region. Make it small. All right, and now let's go ahead and change up the order. And so now what I can say is, oh, hey, instead of going y's left to right, I'm going to go top to bottom when we're talking about x's, and that's also going to be 0 to square root of pi. And then we're going to do, our y's, and our y is going to be 0, and y equals 0, y equals x. And now we're going to do cosine of x squared dy dx. All right, now again, the reason why we'd want to do it is because it's a lot easier when we actually are trying to take the integral of cosine x squared with respect to y first. And so sometimes it's easier to do that, and again, here it is. So we're going to go ahead and do that. And we're going to get y cosine x squared dx from 0 to x. And so we're going to just get the integral of square root of pi 0 x cosine x squared dx. Integrate that. That's nice. So the derivative of x squared is just 2x, so we need a 1/2. And then the integral of cosine is sine, so sine x squared from 0 radical pi. Go ahead and plug in radical pi and 0. We're going to get 1/2 sine of pi minus sine of 0. And look at that, we get 0. That's always fun. All right. And that's it. So properties of double integrals. I'm going to let you look at this, and then please just ask questions. But, again, we can break up. If we have two different functions, we can kind of just break it up on the inside. So, again, it's like properties of integral still holds. There's a constant. We can pull a constant out. If we have a function that's greater than or less than another function for all x and y in D, then, the same thing is going to be true for the integral. The double integral of f is going to be greater than or equal to the double integral of g. There's a, union between D1 and D2, and they don't overlap. We can go ahead and break it up, just kind of like what we did in Calc 1 and 2, where you could break up the region and just add up the two parts of the region. Again, we can do the double integral of dA. It's just going to be the area of what D is, and then a region D. And then if m is less than or equal to f of x is less than, if our function is in between m and big M for x and y and D, then what we can do is we can say is that then m is going to be, then we can use the area of our region multiplied by both those m's. All right, and I'll talk about it later when